Take the wingspan of a Boeing 747, stretch it out on the floor of a factory, and imagine a machine that size being asked to never make a mistake wider than a single strand of your DNA, millions of times a day, without stopping. That is not science fiction. That machine already exists, and until recently, exactly one company on the entire planet knew how to build it well enough to matter. Every phone in every pocket, every AI chip powering the tools you use daily, all of it traces back to that one company's production floor in a small Dutch town most people have never heard of. Here is the part that should genuinely stop you. In the middle of 2026, a state-backed company in Shanghai, one with almost no public track record, was quietly reported to have started mass-producing its own working version of that impossible machine. And within days, it had knocked billions of dollars off the market value of the company that was supposed to be untouchable. Not a concept. Not a government promise. A production line. Already shipping hardware. Already being tested inside real chip factories. By the end of this video, you will know exactly how a country locked out of the world's most guarded piece of technology managed to build a working alternative, what it can actually do right now, and why one stock chart tells you more about how seriously to take this than any press release ever could. Numbers like that are exactly why this channel keeps digging into stories other people just skim past. Because the moment you check the sources on something this wild, it either falls apart or it turns out to be even bigger than the headline. This one held up. So if you like watching claims get tested against the facts instead of just repeated, tap subscribe now, because the next update in this race could land within weeks, not years. To understand why this matters, you first need to understand why almost nobody else has ever managed to do it. The machines we are talking about are called lithography machines. Think of them like the world's most extreme stencil printer. A normal stencil lets you spray paint a shape onto a wall. A lithography machine uses light instead of paint, and instead of a wall, it prints a pattern onto a wafer of silicon, a thin, round slice of a special material about the size of a dinner plate. That pattern becomes the wiring of a computer chip. The catch is the size of the details. We are not talking about lines you could see with your eyes. We are talking about lines so small that billions of them fit onto that single dinner plate-sized wafer. Getting light to draw shapes that tiny, over and over, thousands of times a day, without a single mistake, turned out to be one of the hardest engineering problems humans have ever solved. For a long time, one company solved it better than anyone else. That company is ASML, based in the Netherlands. ASML started out in 1984 as a small joint venture between the electronics company Philips and a chip equipment maker, and for its first 15 years, it looked like just another player in a crowded field. Then it made a bet almost nobody else was willing to make, pouring roughly $9 billion and about 30 years of research into a version of lithography that used extreme ultraviolet light, a wavelength so short and so hard to generate that most competitors considered it a scientific dead end. ASML kept going anyway. Over that time, it built a kind of monopoly that is almost impossible to find anywhere else in modern industry, not because it kept secrets in a vault, but because the problem itself was so brutally difficult that competitors kept trying and kept failing. Japan's Nikon and Canon both tried, and eventually stepped back to only building older, simpler tools. Intel, one of the biggest chip companies on Earth, tried building similar technology in-house decades ago and gave up. Today, a single one of ASML's most advanced EUV machines costs more than $200 million. Only about 5 chipmakers on the planet can afford to buy and operate one, and the company still leans on a global web of roughly 5,000 specialized suppliers just to build each machine, including lenses from a single German company that took 15 years to perfect. When the most advanced version of this technology became the only way to make the fastest chips in the world, ASML became the single point that the entire global chip industry had to pass through. That is exactly why, starting in 2019, the Netherlands, under pressure from the United States, blocked the export of that most advanced EUV machine to China. Not a single one has ever been sold there. If you were in charge of China's chip industry, watching that door slam shut, knowing the company on the other side of it had a 30-year head start, what would you have done next? You would have done exactly what China did. You would have poured money and engineers into every alternative path left open to you, and you would have picked the next best tool available, one step down from the banned machine called Deep Ultraviolet Lithography, or DUV. DUV is older technology. ASML has been shipping DUV tools since the late 1990s. It is not banned the way EUV is because it is considered less advanced. But here's the twist that made 2026 such a strange year for the chip world. DUV, when it is pushed hard enough, using a clever multi-step trick, can still make chips good enough to run real AI workloads. It's not the newest hammer in the toolbox, but if you know how to swing it right, it can still drive some very serious nails. So the real question was never whether China could build any lithography machine. It was whether China could build one good enough, reliable enough, and in high enough numbers to actually matter inside a real factory. Think of it like the difference between building one race car by hand in a garage and running an entire assembly line that turns out 100 identical race cars a year, every one of them safe enough to actually put a driver behind the wheel. Plenty of engineers around the world have built one impressive prototype. Almost none have managed the second part. This is where the story gets interesting, because for years the honest answer from most experts was no. China's homegrown lithography effort actually started decades ago. The country's main state-backed toolmaker, a company called SMEE, short for Shanghai Microelectronics Equipment, was founded all the way back in 2002 as part of a national research push. For years afterward, its machines existed mostly on paper and in academic testing. A widely repeated line from a Chinese semiconductor executive a few years back summed up the mood at the time, describing homegrown lithography tools as checked and approved by researchers, but never something an actual chip factory dared to switch on. That is a brutal thing to say about your own country's flagship equipment maker, but it captures just how far the theory was from the factory floor. So picture the mechanism like this. Imagine you are trying to draw the most detailed map ever made, but you can only use a giant overhead projector and a razor-thin beam of light. First, you shine that light through a mask, which is basically a stencil with the chip's circuit pattern cut into it. The light passes through the open parts of the stencil and lands on a chemical coating on the silicon wafer below, kind of like how sunlight through a stencil can tan a pattern onto your skin at the beach. Wherever the light hits, the coating changes, and wherever it is blocked, it stays the same. After that, chemicals wash away the parts that were not protected, leaving behind the pattern etched into the wafer. Do this layer after layer, dozens of times, lining up each new layer perfectly on top of the last one, and you slowly build up the full three-dimensional structure of a working chip. Now here is where the truly clever engineering comes in, the part that ASML mastered and everyone else struggled to copy. To draw finer and finer lines, you need to bend the light more sharply, and one way engineers found to do that is by putting a thin layer of ultra-pure water between the lens and the wafer. Water bends light more than air does, almost like how a straw looks bent when you dip it into a glass. That bending effect lets the machine focus a much sharper, much smaller beam onto the wafer than it could through air alone. This trick is called immersion lithography, and ASML shipped its first commercial version of it back in 2004. It sounds almost too simple for something this advanced, water of all things, but that simplicity is exactly why it took years of precision engineering to make it work at a scale of billions of transistors without a single droplet ruining the pattern. Even with that trick, one exposure of light is not always enough to draw the smallest, most crowded patterns modern chips need. So engineers developed a second layer of cleverness called multiple patterning. Instead of trying to draw every detail in one single overlapping mess of lines, you split the pattern into two separate passes. The first pass draws every other line, then the wafer shifts slightly, and a second pass draws the lines in between. Picture painting a picket fence by first painting every other board, letting the machine nudge over by exactly half a board width, and then filling in the gaps on a second pass. Do that carefully enough, and you can pack twice as much detail onto the chip as a single exposure ever could, using the exact same DUV light source that has been around for decades. This is the workaround that companies like China's SMIC, its largest chipmaker, have leaned on to keep producing fairly advanced chips, even without access to the newest EUV machines. It's slower, it's more expensive per chip, because every layer now needs two passes instead of one, and it demands almost inhuman precision to keep those two passes perfectly aligned across a wafer covered in billions of tiny features. But it works, and getting it to work reliably inside a real factory, at real volume, without alignment errors piling up layer after layer, is precisely the hard, unglamorous engineering problem China spent years trying to crack. To put the scale of that precision in perspective, engineers working on EUV machines have compared the accuracy required to firing a laser from Earth and hitting a coin on the surface of the moon, then doing it again a fraction of a second later, and again after that, tens of thousands of times without ever missing. DUV lithography, the older technology China focused on instead, is a notch less extreme, but it is still operating in a world where the wafer cannot be allowed to vibrate more than a few atoms out of place while the light is firing. That is the kind of tolerance where a truck driving past the building or a change in room temperature of a single degree can be enough to ruin a batch of chips worth a fortune. Every single one of those variables has to be tamed before a machine like this can be trusted inside a working factory. So when a new machine claims to be ready for that environment, the real test was never going to be a press release. It was always going to be whether real chip makers were willing to bet their own production lines on it. So who actually cracked it, or at least got closer than anyone expected? According to reporting from the Information in the summer of 2026, later confirmed in broad strokes by Reuters, a Chinese state-owned company called Shanghai Aishengna Electronic Technology Group had quietly begun mass-producing an immersion DUV lithography machine. What made this company notable was not that it appeared out of nowhere, but who it absorbed on its way up. Aishengna pulled in engineering teams from Yuliangsheng, a lithography startup linked to Huawei's chip equipment arm C-Carrier, and from SMEE itself, the state toolmaker that had spent over 20 years trying to get this right. Corporate records reportedly even show Aishengna and Yuliangsheng sharing the same Shanghai address, which tells you this was not one lone genius working in a garage. This was China consolidating years of scattered effort under one national team. And that national team was not just running tests in a lab. Reports indicated the plan was to deliver roughly 5 of these machines by the end of 2026, with about 20 more scheduled for 2027, going to some of China's most important chip and memory makers, including SMIC, Hua-Hong Semiconductor, and Changshin Memory Technologies, a company you might know better by its short name, CXMT. Notably, SMIC had already been quietly testing an immersion system from Yuliangsheng since September of 2025, months before the wider world found out, which means the testing phase, the part where a machine either proves itself on real silicon or gets sent back to the drawing board, had already been running in the background for close to a year. 5 machines and then 20 more might not sound like a lot compared to the roughly 130 machines ASML plans to build in a single year, and it isn't, at least not yet. But manufacturing history is full of technologies that started as a trickle before turning into a flood once the early bugs were worked out. The first ASML immersion tool in 2004 did not immediately replace every older machine in every factory either. It took years of incremental trust building before immersion lithography became the industry standard it is today. The real number worth watching over the next 2 years is not how many machines ship in year 1, it's how steep the curve looks by year 3. Numbers tend to tell the truth faster than press releases do, and the numbers here are worth sitting with for a second. When the news broke, ASML's stock did not just wobble, it dropped as much as 8% in a single trading session, wiping out a meaningful chunk of market value in hours. That kind of reaction does not happen because investors think a story is nothing. It happens because investors suddenly have to price in the possibility that ASML's grip on the Chinese market, which accounted for about 14% of its net system sales, or roughly $1 billion, in the second quarter of 2026 alone, might not be permanent anymore. Zoom out even further and the trend looks even sharper. China had made up around a third of ASML's total sales in 2025, and tightening export rules were already expected to shrink that share down toward roughly a fifth of the business by the end of 2026, even before this new domestic machine entered the picture. Meanwhile, ASML itself was not standing still. The company had been planning to build around 130 DUV immersion machines in 2026, with capacity set to grow by another 30% in 2027, a reminder that even the company being challenged was scaling up as fast as it could, protecting the parts of the world where it still faces no real competition at all. So which side do you think blinks first in a race like that? The challenger trying to prove reliability one wafer at a time, or the incumbent trying to defend market share with sheer production volume and 30 years of trust already banked? But before you picture factories across China suddenly humming with fully homegrown chip tools, it's worth looking at where this technology already has feet on the ground, because the proof is not just in the announcement, it's in what came before it. SMEE, the older state toolmaker whose engineers helped build the new machine, delivered its first production-capable 28-nanometer DUV immersion tools to Chinese fabs back in late 2023. 28-nanometer is not cutting-edge by today's standards, but it is a real, usable manufacturing node, used in everything from car chips to older generation smartphone processors. That was proof, years before the 2026 headlines, that a domestically built lithography machine could actually sit inside a working factory and produce real, sellable silicon, not just survive a lab demonstration. One of SME's newer tools was reportedly even given a name tied to Wang Shiji, a legendary ancient Chinese calligrapher known for impossibly precise flowing brushstrokes, a small but telling detail about how the engineers themselves see the connection between drawing a perfect character with ink and drawing a perfect circuit with light. None of that proof came easily, and it definitely did not come quickly. SMEE was founded back in 2002 specifically to chase domestic lithography as part of a national research program, and for the better part of 2 decades the results were modest at best. That first serious attempt at a homegrown DUV machine, launched under that same early program, did not end in a working product at all. It simply ran out of runway. It took roughly another 20 years of steady, mostly unglamorous funding, testing, failing, and rebuilding before SME's 28-nanometer tools were considered stable enough to actually ship. That timeline matters because it shows this was never a sudden breakthrough dreamed up in a single lab overnight. It was a slow grind, the kind that rarely makes headlines until the day it suddenly does. Which raises the obvious next question. If 28-nanometer tools took roughly 2 decades to become reliable, how much faster could a machine capable of feeding SMIC's most advanced production lines actually move from prototype to full trust inside a real factory? Zoom out from the factory floor for a moment, and you start to see why this story is not really about one machine at all. For years, the global chip industry operated on a quiet assumption that no matter how much money or ambition any single country threw at the problem, extreme ultraviolet and advanced DUV lithography would remain a Dutch and Japanese specialty, and everyone else would simply have to buy in or fall behind. That assumption shaped trade policy, national security strategy, and trillions of dollars in stock market value. A credible, even partial Chinese alternative does not need to be as good as ASML's best machine to change the equation. It just needs to be good enough, cheap enough, and available in enough numbers that Chinese chipmakers are no longer entirely at the mercy of export restrictions written in Washington and The Hague. That is the kind of shift that reshapes how countries plan their next decade of technology policy, not just how one company's balance sheet looks next quarter. And this is not happening in isolation. It's landing in the middle of a much bigger contest over who controls the tools that build the future. The chips that will run artificial intelligence, autonomous factories, and whatever comes after that. Every country involved understands that whoever controls the machines that make the chips effectively controls the pace at which everyone else gets to build. That is why a single report about a state-owned Shanghai company absorbing a few smaller startups made headlines from Beijing to Wall Street within days. It's rarely just about one machine. It's about who gets to set the terms of the next 20 years of computing. And for the first time in a long time, the answer to that question is genuinely not obvious. Think about what it means for a country to no longer be entirely dependent on machines it cannot buy from anyone else. Export controls only work as a strategy if the country on the receiving end has no other option. The moment a credible domestic alternative exists, even an imperfect one, the entire calculation behind those restrictions starts to shift. Governments that spent years designing careful rules about exactly which machines could and could not leave Dutch or American soil now have to ask a much harder question, whether those rules are still doing what they were built to do, or whether they mostly succeeded at motivating the very breakthrough they were trying to prevent. That is not a comfortable position for policymakers to sit in, and it is exactly the position this story has put them in. For chipmakers outside of China, there is a quieter kind of pressure building too. If Chinese factories can eventually produce advanced enough chips using homegrown tools at a lower cost, sold to a domestic market of over 1 billion people, that changes the competitive landscape for everyone building phones, cars, and AI hardware around the world, not just companies operating inside China. Competition has a way of pushing every player in an industry to move faster, cut costs, and take fewer years between breakthroughs. Whether that competition ends up being healthy or destabilizing for the global chip supply chain may end up being one of the defining industrial questions of the next decade. Now here is where it would be easy for a video like this to get carried away, so let's slow down and be honest about where the real limits still are, because the story only stays trustworthy if we tell you the parts that are not finished yet. Multiple analysts, including a team at the research firm SemiAnalysis, pointed out that a working prototype and a fully scaled, reliable production fleet are two very different things. Building one impressive machine in a clean room is genuinely hard. Building dozens of them that all perform consistently, day after day, inside multiple different factories, with a support ecosystem of spare parts, trained technicians, and software behind them, is a different and arguably harder challenge, one that analysts specifically flagged as the most underestimated part of the entire effort. On top of that, these new Chinese tools have to compete economically against ASML machines that Chinese factories have already owned for years and already paid off, machines whose costs are, in accounting terms, essentially free at this point compared to a brand new domestic tool still working out its bugs. There is also the plain matter of the technology gap itself. Even Chinese industry commentators, quoted in outlets covering the story, describe the new machines as still lagging ASML by what some called roughly 4 generations of development, a gap that does not close overnight no matter how much national attention or funding gets thrown at it. 4 generations might sound like a small number, but in an industry where each generation can represent close to a decade of accumulated refinement, in optics, in chemistry, in the software that keeps thousands of moving parts perfectly synced, that gap represents a genuinely enormous amount of engineering ground still left to cover. SMEE's own public track record backs this up. Even after more than 2 decades of work, the company's global market share in its strongest category, older I-line lithography equipment used for legacy chips, sits at only around 4% worldwide, according to research from the Center for Strategic and International Studies. That is a company that has made real, documented progress and is still, by its own numbers, a small player on the global stage outside of China's borders. On top of the technology gap, there is a trust gap. Chip factories run on razor-thin margins for error, and swapping in an unproven machine risks ruining an entire batch of wafers that can be worth millions of dollars each. That is exactly why some Chinese chip makers have historically shown real reluctance to fully commit to domestic tools, even when national pressure encouraged them to, because a factory that stops producing chips for even a few days can lose far more money than it ever saves by avoiding an ASML purchase order. Reliability in this industry has to be earned one flawless production run at a time, not announced in a single press cycle. So is this the beginning of a genuine shift in who controls the world's chip supply chain, or one impressive but limited step in a race that is still going to take years to settle? Right now, honestly, both things are true at once, and the honest answer is that nobody, not the analysts, not the companies involved, and certainly not anyone promising you a confident prediction in a video like this one, actually knows for certain which way it tips first. Here is the short version, if you strip away everything else. China spent years locked out of the world's most advanced chip-making machines, took the next best available path, combined scattered engineering teams into one focused effort, and produced a working, deliverable immersion DUV lithography machine that real factories are now testing on real silicon. It is not a replacement for the banned EUV machines, and it is not yet proven at the scale that would truly threaten ASML's global dominance. But it is real, it is documented, and it moved fast enough to knock billions off a European stock in a single day, which tells you the rest of the world is not treating it as a rumor. If a story like this deserves anything, it's a bit of your time to hit like on the way out, and subscribing with notifications turned on means you will be there the moment the next report on this race breaks, because judging by how fast this year has moved already, the next update might come sooner than anyone expects. So here's the question worth typing into the comments. If China's homegrown lithography machines keep improving at this pace, do you think global chip makers will actually start choosing them over ASML's tools within the next 5 years? Or will trust in a totally unproven supply chain keep holding them back?